Welcome back. We're still in Chapter 6 talking about covalent compounds, and today we'll look at Lewis structures. Lewis structures are models that use electron dot structures to show the arrangement of valence electrons in molecules. When we draw Lewis structures, we're going to use lines and dots. The lines will represent bonding electrons or shared pair electrons. These are the two electrons that are being shared between two different atoms in a molecule. So again, we'll use lines. They're basically the bond. So the lines represent the bond between two atoms. The dots are used to show lone pairs. Remember, the lone pairs are the electrons that are not involved in bonding. And so we always pair the dots up, and we also use those in the Lewis structure. The rules for writing Lewis structures are kind of complicated until we start practicing them. But know that we need to calculate the needed electrons, the available electrons, the bonding electrons, and then the lone pair electrons. And this is a slightly lengthy process, but it will save you some headache and guesswork later. So when we calculate N, the needed electrons, it is the sum of the electrons needed for all atoms to be stable. And all atoms will need 8 except hydrogen, beryllium, and boron. On your periodic table, go ahead and write the exceptions. So on your periodic table, write exceptions: H equals 2, Be equals 4, and B equals 6. When we do our calculations, if we have hydrogen, beryllium, or boron as an atom in the compound, we have to use these numbers and not the 8. All other numbers, or all other elements, will use 8. The second step is to calculate A, the available electrons. These are the valence electrons that each atom are contributing to the molecule. So it's the sum of all valence electrons present. Polyatomics have a special step because remember, with a polyatomic ion, we are changing the number of electrons. And so if we have a negatively charged ion, an anion, we have to remember that we gained electrons. So we're going to add the number of electrons gained into our total for A. The opposite is true for cations, the positively charged ions. Remember, we lost electrons in a cation, so we need to subtract the number of electrons from the total in A. Now that we have N and A done, that's what we need to finish the rest of our calculations. For B, the bonding electrons, this is the difference between N and A. So we're going to take what we calculated for N and subtract what we calculated from A from it. And that will give us the number of electrons involved in bonds. Because this is the total number of electrons involved in bonds, to get the number of actual bonds, we have to divide it by 2. This will tell us how many lines we will use in the Lewis dot structure, or in the Lewis structure. L are the lone pair electrons, and we're going to treat that similarly as we did B. It is the difference between A and B, so you take A and you subtract B from it. Remember though, the B that we're interested in was the first calculated B, not the divided B. We want to know total electrons here. So once we have done that, then we will divide that calculated L by 2 to obtain the number of lone pairs. This is how many paired dots we're going to use in our Lewis structure. Now that we've calculated the N, A, B, and L, we're ready to draw the Lewis structure. And the first thing we'll do is to determine the arrangement of the skeletal structure. How will we place the different elements of a compound? In general, the least electronegative element, which is usually written first, is the central atom. You could also think of this as the atom that has the smaller group number or can make the most bonds. Something to remember, though, is that we never have hydrogen or a halogen as the center. Hydrogen can only make one bond, and the halogens also can only make one bond. So we will not place those in the center. And also, another hint is that C, carbon, it's almost like it stands for central. If carbon is present in an atom, it will always be the central atom in your diagram. And also try to create your model as symmetrical as possible, and do this in a linear fashion. That'll make sense as we practice. Once we've arranged our elements, we're going to connect them to the central atom. So we're going to use a line and connect each of the surrounding atoms to the central atom. Then we need to verify that the number of bonds in that skeleton match the calculated number from B. If, for instance, it said we needed 4, but we only drew 3 to connect, then we need to add another bond, a double bond, in our Lewis structure. So we'll use double and triple bonds when and where necessary. And then again, halogens and hydrogen can never have more than one bond. Our last step is to use pair dots and place them around the attached atoms first, so that each has an octet except hydrogen, which only has one bond and will have absolutely no dots. Beryllium and boron will also not have an octet, remember, because they are exceptions. Once we have placed all of our lone pairs around the attached atoms, we will place any remaining lone pairs around the central atom at that time. Alright, so we'll actually get to see those rules in practice, and then they'll start to make a little bit more sense as we draw Lewis structures. Alright, remember, when calculating N, this is the total electrons needed for that molecule. And so in order to get to that, we have to remember that all atoms need 8, except for hydrogen, which needs 2, boron, which needs 6, and beryllium, which needs 4. So those are our exceptions. All others need 8. Okay, so we need to identify the elements involved and then the number of atoms per element and multiply that by the needed number. So we have nitrogen. There is 1 atom of nitrogen. Nitrogen needs 8. We multiply this across for 8. We have 3 atoms of fluorine, and fluorine needs 8. Now we know that these need 8 because they're not one of our exceptions that we listed above. That gives us 24. We're going to add these down to get the total number of 32 electrons needed. The available electrons, we are going to remember that this is the valence electrons. So this is how many electrons are already available to us. So again, we have 1 nitrogen atom. Valence electron number for nitrogen is 5. Multiply that across. There are 3 fluorines. The valence electron number for fluorine is 7. Multiply that across. Add these down for a total of 26 available electrons. When we are looking at B, these are our bonding electrons. This is N, which was 32. We already calculated it. Minus A, which was 26. We're going to subtract these two numbers, and we get a total of 6. Now that is telling us that there are 6 electrons involved in bonding. But remember, a bond is going to be represented by a line, and technically there is 2 electrons per bond. So in order to get the number of bonds, we need to divide the 6 by 2, and that will give us 3 bonds for our Lewis structure. Calculating L, we're looking for A minus B. So A was 26 again, and we're going to subtract B from it. We're going to use the 6 that we calculated earlier. So we're not using the number of bonds, we're using the number of bonded electrons. So we subtract these two numbers and we get 20. That tells us that there are 20 electrons involved in Lewis, or the lone pairs. We need to know how many lone pairs that is, so we're going to divide that by 2 again, and that tells us there are 10 lone pairs. Lone pairs are these. Okay, so now we're ready to draw our Lewis structure. The first step is to determine the arrangement, the skeletal arrangement. And we have to determine what element is going to be center. And we said it was the least electronegative, or the one with the lowest group number. And that happens to be N, which is listed first, because they are usually listed first. And we want to set them up so that they're symmetrical as possible. So I have 3 F's that I also need to place in my diagram. So I'll go left, right, bottom. That's the pattern I usually follow, is left, right, bottom, top. The next step is to draw bonds connecting each atom to the center atom. So I've got a bond here, and a bond here. And remember, each bond represents 2 electrons. I count the number of bonds, 1, 2, 3, and I verify that that's the number I calculated. So I'm good to move to the next step, which is placing lone dots, the lone pairs. Alright, it says that I need a total of 10, but what I'm trying to do is place them around the attached atoms in such a way that each of those atoms have their octet, or their needed number of electrons. Remember, each bond represents 2, so fluorine already has 2, and it needs a total of 6 more, or 3 lone pairs. Alright, and that's going to be the same for each of these fluorine atoms. I count the number of lone pairs that I've used, 1, 2, 3, 4, 5, 6, 7, 8, 9, and I check it against my calculated number, which says 10. So there's 1 lone pair left. That's the lone pair I will place on center. And then I need to just double check that each of these atoms have their octet. So knowing that a bond is 2, we look at each of the fluorines, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. So all of our fluorines are good. Then we look at nitrogen. Each bond represents 2, so I have 2, 4, 6 in bonds, and then the last 2 are in the lone pair for 8. This one is done. Alright, this next example is carbon tetrachloride. I start with N. N is the needed electrons. I identify the elements, the number of atoms, and their needed number. So I have 1 carbon atom. Carbon needs 8. I multiply that across for 8. I have 4 chlorine atoms. Each chlorine atom needs 8. I multiply that across for 32. I add these and I get a total of 40. In my available column, this is my valence electron number. So again, I have 1 carbon, Carbon's valence electron number is 4. I have 4 chlorines, and each chlorine is 7. Multiply that across for 28. I add these down, and I get 32. When I look at B, I take the 40 for N, and I subtract from it the 32 for A, and that gives me 8. That is 8 electrons involved in bonds. I divide that number by 2 to get 4 bonds in my Lewis structure. For L, I take the 32 from A, and I subtract the 8 from B, and that gives me a total of 24. There's 24 electrons involved in lone pairs, and I only have 12 lone pairs because I'm going to take 24 and divide that by 2. So I am ready to draw my structure. C, remember we said anytime carbon is present, it's almost like carbon, that C stands for center. So carbon will be in the center. And then I have 4 chlorines. So left, right, bottom, top. So here's my skeletal structure. The next step says that I need to connect each atom to center by drawing a bond. 1, 2, 3. There are 4, so that is confirmed. And then the last step is to draw our lone pairs. And we have a total of 12 lone pairs that we're going to use. We look at chlorine, and it already has 2 involved in a bond. We needed a total of 8, so that means I need 6 more, which would be 3 lone pairs.
Hello, guys.
So I'll add my lone pairs to my chlorine atoms, and then count. I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that number is confirmed. And that is carbon tetrachloride. Sorry. So to get some buy-in from you for doing the work, because these are pretty easy, but they do take a lot of time. And we do so many of them so that you know exactly what to do. It becomes a habit, a pattern, that you get really sick of them. So let me show you why we do the work. If I was just to predict the shape of this, and if I was in class, I'd have you predict the shape of it, more than likely you would have drawn this structure. You're not writing this, by the way. You would have drawn it like this as far as your skeleton, and then based on what we've been doing, you would have done this, and then probably finished up like that. So we're just going to keep this in the back of our minds. This is probably what we would have drawn if we did not use the NABL boxes. So let's see how it would actually realistically look. I should say theoretically look, but alright, so looking at calculating N, there's 1 carbon. Carbon needs 8. There are 2 fluorines. Fluorine needs 8. And there's 1 sulfur. Sulfur needs 8. We add these up and we get a 32. For the A, we have 1 carbon, has 4 valence electrons. There are 2 fluorines with 7 valence electrons. And we have 1 sulfur with 6 valence electrons. We add those together, we get a 24. Calculating B, we take N, we subtract A, and we end up with 8. We divide that by 2, and we know we have 4 bonds. we're going to take our 24A and we're going to subtract B, and this is going to give us 16 electrons involved in 8 lone pairs. We're ready to work on the structure. We would put carbon in the center. Since we want it to be symmetrical, we'll go ahead and put the 2 fluorines on the left and the right, and follow that with the sulfur on the bottom. We're going to connect them using bonds, and then we check. We have 3, but we need 4. So that means that this has to have one more bond. If we remember from our rules, or going back through our rules, we see that the halogens can never be multiple bonded. So fluorine cannot receive that second bond, but sulfur can. So we're just going to draw another bond connecting sulfur with carbon. Now we have the 4 bonds we needed, and we are left with lone pairs, and we have a total of 8. So we're going to just start with our surrounding atoms. We have 2 in our bond of fluorine, so fluorine needs 3 lone pairs. Same for this fluorine. We look at sulfur. Sulfur already has 4 electrons because it has the 2 bonds, and there's 2 electrons per bond. So it has 4. It will need 4 more, and it will get those with its lone pairs. So we count the lone pairs: 1, 2, 3, 4, 5, 6, 7, 8. Our structure is now complete. We would confirm by checking that each electron, or that each atom, has its needed number of electrons, which it does, and then we'd be done. And it definitely does not resemble our predicted. So this is not what it would look like. And that is why we take the time to calculate NA, B, and L, is so that our diagram is easy to construct. This will be the last practice that we're going to do today in this section of notes. So once we finish this slide, our notes are done for today, and we'll start with our worksheet. So we will come back to finishing up these notes next class. I have 2 nitrogens. Each nitrogen needs 8. That gives me a total of 16. When I look at A, I have 2 nitrogens, and nitrogen has a valence electron number of 5, which gives me a total of 10. And technically I guess I could have put this here, but since I only have the 1 element involved, there's really no addition, so I'm just writing the numbers down on the bottom. I'm going to take the 16 and subtract the 10, and that will give me 6 electrons involved in 3 bonds. Then I'm going to take A and subtract B, and that gives me 4 electrons involved in 2 lone pairs. Setting up my skeleton, since there's only 2 atoms, we're going to do the side by side. We're going to connect them. I count my bonds. I've used 1, but I need 3. Well, there's only one place to put all 3 of these bonds in this structure, because bonds always have to connect 2 atoms together. You cannot just put them anywhere. And so I will go ahead and make that a triple bond for N. And now our lone pairs, we have 2 of them, and since this looks identical, we're going to go ahead and give each N one of those 2, and we have it where it looks symmetrical, and then we can double check. We have 2, 4, 6, 8, because there's 2 electrons involved in a lone pair, and then we have 3 bonds where there's 2 electrons each, so that gives us 8 for each of our ends. And so this will wrap up our practice. So we've covered the rules for drawing Lewis structures, and then we've practiced the simple molecules and the multiple bond molecules, and then next class we will finish up the other 3 types that are located in your notes. Please make sure you watch the next video that shows the practice problems, the sample problems for your worksheet. Alright, see you next time.